Hello and welcome to Lab 7. So to review, Lab 5 was all about getting water into the atmosphere, so humidity. Lab 6 was about taking that water that was gas and turning it into a liquid or a solid, so making clouds, so condensation for Lab 6. And Lab 7 is all about precipitation. And so what we're going to be using again is that table that we've been seeing, and they've repeated it down here in figure 1-7. And now we're going to get a little bit more specific, and instead of just looking at whether the atmosphere is unsaturated or supersaturated, or if it's the line itself, it's 100% saturation, right? So this is the 100% mark for saturation is this line. We're going to be looking at a new line that talks about whether it's going to be ice or water. And so this is down here in this figure down below, gives us our saturation specific vapor pressures. And if you are above this solid line here, you're going to be liquid water. If you're below this dotted line here, you're going to be snow, ice, something that's solid. If you're somewhere between the dotted line and the straight line, it really just depends on whether you're closer in percentage to the dotted line or if you're closer in percentage to the solid line to determine whether you're going to be liquid or solid in your vapor pressure. And so question 1 says consider an air sample that's denoted by the asterisk, so the little star down below in figure 7-2. The temperature is -15 degrees Celsius with a vapor pressure of 1.27 millibars. What is the relative humidity with respect to the water if at -15 degrees Celsius the saturation vapor pressure over liquid water is 1.91 millibars? So this is a percentage. They're asking for what percentage vapor pressure. And it's a really simple setup, simple equation layout, where we're going to take the vapor pressure itself, and it will go over the saturation vapor pressure. And then we will times that by 100. So taking the numbers off the chart, they said that the vapor pressure is 1.72, and they're literally reading that off the chart. They're taking this little dotted line and they're bringing it over, and where it lines up is 1.72. And that will be divided by 1.91, and they're reading that off of, if I lined up my little asterisk where it hits the liquid water line and I read that off, it comes out to line up there. And so that's where they're getting those. That's the unit of millibars of pressure and millibars of pressure. And I'm going to times that by 100 to get my percentage. And when I do that, the answer will be 90. So 90%. Question 3 asks, what is the relative humidity with respect to ice if at -15 degrees Celsius the saturation vapor pressure over ice is 165? So for this one, I'm not going to give you the answer to this one, but I will clean up the board and just show you how you're going to lay out the problem. So it's the same equation, except for your saturation vapor pressure will be that of ice. So the water itself, the liquid material in the condensed cloud, is still 1.72 millibars. But now instead of measuring a saturation vapor pressure for the liquid, you're going to read it off the ice. And so you'll plug in 1.65 times that by 100. When you get your answer, you can write that in as percentage for question 3. So question 4 asks what happens to water vapor if, with respect to the surrounding ice crystal in the environment, is supersaturated. Well, this is a bit of a go figure, guys. What do you think will happen if the percentage for liquid water is 90 and the percentage for ice is greater than 90? What do you think is going to happen? Do you think there'll be snow? Write a sentence. Question 4. All right, so questions 1 through 4 we're all about whether it's going to rain or snow. So basically whether you're going to get solids or liquids. Questions 5 on is all about getting the water droplets down to earth and whether they're going to be liquid, solid, big crystals, small crystals. So basically size of the material falling from the sky. And to do that, we need to look at some different things, one of which is the size of the water droplet, so its area, and the volume of the water droplet. The equation you're going to use is this equation right here for the volume. And so question 5, what is the volume of an ordinary cloud droplet? And they give you that size in millimeters. Use the millimeters, not the micrometers, which is the thing with the mu, the 25 mu. And you're basically just plugging it into the equation. So you're going to take 4/3, and that will all be to pi, and the radius, which is 0.025, and that will be to the power of 3. So when we go to do this, do the 0.025 to the power of 3 first, then times it by your pi, then times it by your 4/3. And it kind of depends on your calculator how you're going to get to the power 3. Some of you have a power to 3 button. Some of you are going to be looking for the YX button, and some of them are going to look for this little tilde mark for your calculator. So you've got to figure out the buttons on your calculator and go for it. And I'll meet you back once you've plugged it in. For your answer, it's going to be a small number, and you can write it out in standard form, or you can write it out in scientific notation. So it's going to be a 0.000065, or if you want to move your decimal over, you can move your decimal over and write it in as 6.5 times 10 to the power of 1, 2, 3, 4, 5 to the power of 5. And then this unit, because we did it to 3, will be mm3. So we're going to cube our millimeters. So that's our question 5. You're going to use the same equation to work question 6. And then for question 7, they're going to ask you for the area and the rate of fall. And so for question 7, we're going to work a different equation. So first off, water droplets are funny. If they're liquid and they're falling from the sky, they don't fall in nice clean circles or sweet little teardrops like you learned in school. They actually bend and repose right in the center, and so they end up making these funny little discus shapes that if I cut it, it would be thick on the sides and really thin in the center. Or if I was looking at it from the top, it kind of looked like a white blood cell with sort of a thicker exterior area and a thinner membrane to the middle, like a funky thin disc with a thick outside. It's kind of a funky shape, and this is how the water droplets fall, which means that the area measurements is one that has to take into account how the water droplet will repose or flatten out into a disc-like shape. And so the area equation that you're going to be using to do questions 7 and 8 will be the standard area equation that you learned way back in school, which is area is equal to the pi of the radius to the power of 2. Quickly as a note too, as you're working these problems, if for some reason your calculator doesn't have a pi button, you can always do it to 3.14 because that's pretty close to pi. It's not exactly pi is a longer number than that, but you can use that as a shorthand for pi. And so for question 7, what is the area of the bottom of the falling rain droplet if it is 0.5 millimeters radius? So they're giving you the radius, it's just plugging it into the equation. So I'm going to do pi to the power of 0.5 5 power 2. So you're going to plug that in and get your answer. And I'm going to get my 0.785 mm to the power of 2. So that'll be my unit. So try the same thing for questions 8. And for question 9, it's just asking you a question about what's going to happen if the raindrop is bigger versus smaller. Which one is more likely to reach the ground? And this will be it for part 1, and I'll meet you on video part 2.